तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
The previous lecture we took a look at the concept of memory mapped I/O and also started the discussion of device service on device service routine, specifically with reference to programmed I/O. Now, what is this device service routine? After all, it is a CPU which is involved in executing a program, right. Now, whenever a device needs attention, either the CPU will look and see whether the device needs attention, or the device we said will interrupt the CPU and will demand attention. In either case, the CPU must stop whatever program it is doing, currently executing, and take up a program or what we call as a routine, essentially to service that particular device whichever needs attention. Okay. Now, in the case of programmed I/O, we saw that it is the CPU which takes the initiative, checks for the status of the device and decides whether the device is ready or not. If the device is not ready, it waits. Okay, it waits in this particular loop. I mean, as written in this particular program, it just has to wait. You can also rewrite the program so that if one particular device is not ready, then the CPU goes and checks another device, right. It just depends how exactly you write the program. That is why it is called a programmed I/O. Now, in this particular one, it just waits indefinitely, and then when the device is ready, as indicated by one bit, that is a ready bit in the status word. Okay. We have discussed that in detail. Now, when it is ready, it moves out of this loop and then moves on to service that particular device, in which case it just has to affect the data transfer. Since we have assumed an input device, what we are saying is we are moving the data which is available in the data buffer of the device to the accumulator, which means to the CPU, right. So, that is in other words input. On the other hand, if you happen to have an output device, it is just the other way. What is this? Is for an input device, right, for an input device. If it were an output device, instead of this, okay, so instead of this, what we will be having is just the other way, because of the way we have assumed the format of the instruction, and we had assumed also what, a memory mapped I/O scheme. Just try to recall. Instead of this, we would be having just the other way, that is move whatever we have in the CPU, that is accumulator of the CPU, move, this is the source, this is the destination. You remember the move destination source, this is the format we had followed earlier. So, move what is there in the CPU to the device buffer, which means outputting. Okay. So, this is what we will be having for output device. So, this in fact is the essence of an I/O program. An I/O program would mean granting that the device is ready, making the data transfer. Now, in programmed I/O, CPU checks. Now, we will see this is all that is there in data transfer. Of course, it all depends on the this particular size of the buffer. For simplicity sake, we have assumed a buffer of only one, say character or byte, let us say, assuming the accumulator is also a character or a byte size. So, we are just moving one byte. Suppose the device happens to generate lot of data, right, then we have to put a counter. Suppose it say generates 10 bytes of data, then we have to set up a counter, and then assuming this data transfer is byte by byte. So, we have to keep counting and then checking. After 10 bytes transfer is over, this whole IO program is over. This is how we have to do. It is part of programming. Okay, I will skip that detail. Now, let us move on from this programmed IO to the next scheme. What is the next scheme? The next scheme is one in which the IO the CPU is not taking the initiative. It is up to the IO to interrupt the CPU whenever it is ready. Okay. So, this we are calling it as interrupt driven IO scheme. As per this mode of transfer, since CPU need not check, now go back to this previous program. Okay, go back to this previous program. Now, you see this part is only for checking whether the device is ready or not. So, that is not there now. It is only the data transfer that need be affected, depending on input or output. Okay, the data transfer must be affected. Now, in other words, we say that I may not be showing all the details of the bus here. I will only show the necessary connections between the CPU. We will also not bother about the memory in this particular case. Suppose we have say 2 or 3 IO interfaces, that is one for each device. Well, that is good enough. So, now the IO is going to interrupt. Okay. So, the interrupt input is there to the CPU. The IO, when it is ready, it is putting up the interrupt signal. So, see, the device is not going to check whether the device the CPU is not going to check whether the device is ready. It is only this part that is needed. That is, whenever the device is ready, and when is it ready? When its data buffer is full. Okay? In the case of input device, in the case of input device, the data buffer will be full. In the case of output device, the data buffer will be emptied. Okay? That is all the difference between these. So, we will continue our discussion for input device, and then I will just tell you whenever we have to talk about output device also. So, when the input device data buffer is ready, it is going to interrupt. Now, the CPU is going to stop whatever it is doing, whatever it has been doing, and it has to turn its attention to this service part, device service. Okay. So, we said earlier, in the case of interrupt driven IO, there is a context switch. That is a switch from the main program, main routine to device service routine. Now, because it is coming because it is coming up because of the interrupt, this particular thing may also be called interrupt service routine, interrupt routine. Okay. And CPU handles the situation. So, it is also called interrupt handler. Okay. These are all different names for the same thing. Okay. So, let me list this now. Device service routine, okay, or DSR, or interrupt service routine, okay, interrupt service routine. You may also call it as interrupt handler, okay, so on and so forth. Interrupt handler, these are all names for the same thing. Now, what is it essentially? Essentially, this particular one is going to service the device, and what is the service? The service is just seeing that the data transfer takes place. That is, the device status checking is not there in this case. only because the device is ready it has interrupted the processor. Good. If that is so, what is there in the program? The program will only consist of, that is the interrupt service program or the interrupt service routine will essentially consist of the data transfer part and anything else associated with, as I said earlier, counting of how many bytes and so on and so forth. Agreed? That is, suppose 10 bytes have to be transferred as part of the interrupt service, then 10 times the CPU must take up this data transfer, must carry out the data transfer, assuming only 1 byte is transferred at a time. So, the counting part and all those things are there. So, that will also become part of the interrupt service. Okay. So, other than that, you can now see that the service part is nothing but moving this. So, if you assume that we are dealing with an input device, the interrupt service routine essentially consists of this particular statement, that is input device. So, moving whatever is there in the device data buffer to CPU, of course, not over this line, over the data bus, okay, the data part of the bus, not shown in this figure as such. So, what has been shown here is only when the device, rather how the device interrupts the CPU, that is all that is shown in this particular figure. Okay. The data bus will be connected to this, so that over that it will be moved, and the appropriate read write control signal, all those things will also be there. So, not shown here, we will not bother about it. I hope you follow without any difficulty about that. So, the interrupt service or the interrupt routine, sometimes called just an interrupt program. Now, what is it? It is nothing but the CPU executing a main routine and now the CPU executing something like a subroutine, which is now interrupt routine. Okay. So, there is a context switch. Now, very interesting things arise in this particular situation. What is it? First of all, when you have many devices, how will the CPU know which is the device which must be serviced? This is number 1. Okay, because if you have say 10 devices, you cannot have 10 interrupt inputs to the CPU, especially in the case of microprocessor situation, the number of pins limits that, is it not? So, you may have only 1 or 2, maybe 3, say maximum 5. Okay. We do not have really more than between 3 and 5, fine. In the case of even 1, it should be possible. In the case of only 1 interrupt input, it should still be able to, CPU should be still able to identify which is the device which must be serviced, because this may be a say we talk about input device, no, this may be a keyboard and this may be say a light pen input. Okay. So, the kind of service that is needed for the keyboard is different from the kind that is needed for the light pen. So, the programs are different, leave alone the other electrical interface, okay, leave alone that, the program itself will be different. Good. Now, assuming that the devices, there can be any number, all put a request on a single interrupt input, how will the CPU know what is it to do? We already discussed this earlier. What is it? First of all, the CPU will not allow itself to be interrupted until the end of that particular instruction cycle, that we know. Now, at the end of that instruction cycle, it is going to generate the interrupt acknowledge, correct. This particular signal comes at the end of that. Now, one scheme can be that the interrupt acknowledge signal that goes to one device and then to the other device and then so on. Now, shown this way, what does it mean? You may be having n devices, and any one of these n devices may generate an interrupt signal. At the end of that instruction cycle, when the interrupt acknowledged signal is generated, this is the device which is going to get the interrupt acknowledged signal first. Suppose if this is ready, right, we do not have to know when exactly this became ready. When the interrupt acknowledged signal comes, if this is found to be ready, this will respond. And what is the response? So, it has to essentially identify itself, that is, it has to generate a code to the CPU, right. That is, we call that, we call it by what? A vector, right, a code. And what is that code? The code essentially points to where its interrupt service program is, where its interrupt service program is. Okay. So, let us say for the first device, the interrupt service program is starting from location 100. For the second device, it starts from location 200 and so on. For third device from location 300. Essentially, the device must, this device must say my service program starts from location 100. So, it has to send a code which will link, which the CPU will make use of and link it to start address 100. And this second device will have to generate a code, and then the CPU from that it will understand, it will have to link start the service program from 200 and so on and so forth. For instance, the simplest thing, this device itself can put that address 100 which can go. This device can itself put 200 when in response to the interrupt acknowledge. Now, see, after all, an instruction cycle consists of many states. Now, it is possible that we will just say this is one instruction cycle. Okay. It is possible that after all this is time axis, no, time axis. Now, it is possible that device 1, let us say device 2 generated interrupt at this point in the instruction cycle, and device 1, we have just considered 2 devices. So, we will continue just, and device 1 has generated an interrupt at this instant. Now, this is an interrupt signal time at which the device 2 generated the interrupt. Okay. And this is the time in which device 1 generated the interrupt. So, in either case, both have generated the interrupt input has come to the CPU, and the CPU responds with an interrupt acknowledged only at the end of the instruction cycle. Now, by the time we reach the end of the instruction cycle, we see that device 1 is ready, that is why it has interrupted. And so, now you can see, even though device 2 has generated an interrupt earlier, right, when the CPU responds, it sees device 1 as ready. So, immediately this device, okay, device 1, okay, I just said device 1, I think you all followed. This is device 1 and this is device 2. Okay. The first one. Now, both are ready, and since CPU says that this is ready, so this IO device will generate, okay, over the data bus, actually it will send the code and identify itself as its service program is from such and such, and the service program, this is all essentially moving the data. So, the service program for this starting from 100 will be executed, and at the end of it, let us say assume, at the end of that service, it need not be always at the end, we will see why. At the end of the service, device 2 will still be waiting, is it not, because that is also ready and it had not been served. So, at the end of that, device 2 will be served. Now, this is one simple way of looking at it. So, now we will not go into certain issues in this. I said at the end of device 1 service, device 2. and I also said it is not really necessary. We will talk about it, we will come to that a little later. Now, why is it that device, even though device 2 generated the interrupt signal earlier than device 1, why is it that device 1 was serviced first? Mainly because this is the route by which the interrupt acknowledged signal goes. In other words, this is nothing but hard wiring of the priority of the device, right. This is nothing but defining the priority of this device. How? By hard wiring, because it has been hardwired this way. The acknowledge first goes to this point, electrically this goes. So, we also say that device 1 is electrically closer, okay, because of the hard wiring. The device 1 is electrically closer to CPU. I hope you understand why we say electrically closer, because device 1 may be physically farthest. For instance, if the interrupt acknowledge first goes to device 2 and then it comes to device 1, then we would say device 2 is electrically closer, though physically it may be further away, right. Good. So, the priority of device 1 service is high, mainly because we have achieved it by hard wiring the acknowledgement. Okay. Now, by this hard wiring we see that device 1 is electrically closer to CPU, and that is the reason why device 1 was serviced first. We already seen what the service is. Service is essentially data buffer moving, okay, moving the contents in the data buffer. Now, this particular arrangement is also called a daisy chaining. So, it is something like chaining all the devices. Okay. So, take the signal through one device, take the signal through one device, okay, and then through another device and through another device. So, create in fact a chain, right, create a chain. So, this particular thing is also called a daisy chaining. All right. So, this is one way in which the priority can be defined. Now, are there other ways of defining the priority? Obviously, the moment we say through hard wiring, that is hardware, we define the priority, that means there must be another one, maybe through software you may be able to define the priority. Now, how? Right? How is it? Now, let us go back to the original situation itself. Device 2 generated the interrupt and then device 1 generated the interrupt, we said, and at the end of the instruction cycle, when the interrupt acknowledge goes to device is generated by the CPU, it goes to device 1 first, and so device 1 service is taken up. Now, we had assumed a simple one line interrupt service program. Now, assuming that this consists of say some 5 instructions. Okay. Suppose the device service routine, that is the interrupt service routine, specifically in this case we can call it as interrupt service routine. No? This interrupt service routine suppose consists of 5 instructions. That means essentially 5 instruction cycles will be gone through. Now, what did we say earlier? We said that whenever there is an interrupt, at the end of the instruction cycle the interrupt acknowledge will be generated. Now, device 1 service we say consists of 5 instructions. So, 5 instruction cycles. Now, the moment the first instruction cycle of the interrupt service for device 1 is taken up, if this interrupt is still there, what will happen? Okay. After all, from CPU's point of view, it will respond whenever there is an interrupt, and in this particular case the device 1's request had already been responded. and it is servicing, that is, it is executing a program, whether it is a main program or a interrupt service program, it is just a program, no. And the interrupt acknowledge has gone to device 1 and the service program has been started. So, it will be meaningful to assume that this device itself cannot interrupt itself again. So, this interrupt say input would have been cleared. Now, this interrupt signal will not be there and CPU will see this interrupt signal when, that is, the device 1 service has started and it is going through the first instruction cycle, and at that instant it is meaningful to assume that this interrupt input will not be there. Now, this interrupt input will be there. Now, CPU, after it finishes one instruction cycle for device 1 service, will be interrupted because device 2 shows the interrupt input, that is, it has flagged the interrupt input. Now, what happens? The device 1 service has been interrupted, mainly it is just a program, okay. As long as the instruction cycle is completed, it can be interrupted. So, that can be interrupted and device 2. Now, what happens to our earlier priority definition, right? So, now we have to talk about two things. One is, what is the priority before the interrupt and what is the priority while interrupt program is run. That is what we talk about as a hardwired priority, that is as in this, and then what is the priority in service. Okay. So, we have to talk about the two priorities, hardwired priority. Of course, there is a way in which this problem can be circumvented, but anyway, let us make note of this also. In service priority, it is already a device is being serviced. In service, what is its priority? Okay. Now, if we want device 1 service to be completed, what did we assume? We assumed that the device 1 service involves 5 instructions and so 5 instruction cycles. Now, throughout these 5 instruction cycles, if the interrupt itself is disabled, then device 1 service can be completed, no. So, that would be needed sometimes. So, we have to also talk about enabling or disabling the interrupt structure, enabling interrupt structure, that is, the CPU should not respond, I mean CPU is enabled to respond, and in this case disabling interrupt structure, the CPU is disabled from responding to the interrupt. Actually, there are instructions called enable interrupt and disable interrupt. By executing these enable interrupt and disable interrupt instructions, the structure can be enabled to respond to an interrupt input or disable. Now, let us go back to our original problem. Device 2 and device 1 both interrupt. At the end of an instruction cycle, the interrupt acknowledge is generated, device 1 interrupt service is taken up. The very first instruction in device 1, if it were enable disable interrupt, okay, the very first instruction when device 1, the very first instruction in the device 1 service, if it were disable interrupt, then what will happen? No more interrupt will be accepted by the CPU. and the very last instruction of device 1 interrupt service can be enable interrupt, in which case that instruction will be completed, and then only at the end of that instruction cycle only the interrupt input will be honored, in which case we can complete the device 1 interrupt service and then respond to anything. So, enabling interrupt structure and disabling interrupt structure, of course, where in the CPU, right? The CPU, that is how is it done? It is done by having the instruction, it is part of the instruction set of the CPU, okay, and by including this in the service program, in the service routine, we can selectively enable and disable and then keep redefining, or rather in this particular case we maintain the priority. Okay. Now, the same thing holds good. Suppose device 1 and device 2, let us assume that is device 1 and device 2 they generate interrupt at different time. How is it? Let us say only device 2 has interrupted, and to start with device 1 has not interrupted, then device 2 service will be taken up. And if the interrupt has not been disabled, then at any time when device 1 interrupts, then device 2 service will be interrupted, device 1 will be taken up, mainly because of the hardwired priority. Okay. So, this the interrupt acknowledge will be generated. Now, even though by hardwiring we have assumed that device 1 interrupt will be taken up first, suppose during device 2 service the interrupt structure has been disabled. Okay. Suppose during device 2 service, if the interrupt structure has been disabled, how? By executing a disable interrupt instruction as part of the device 2 service program. If it has been, then even though device 1 has a higher priority, because the structure is disabled. So, during service we can keep redefining the priority, and there are many other ways also, by having a separate priority arbitrator and so on so forth. Okay. That is, through software we can keep redefining the priority. That is why we say we have a hardwired priority and then we have in service priority, and this particular thing can be changed. What can be changed is what can be done through software. The one which is hardwired can never be changed. All right. So, right now there are many ways. We assumed only one interrupt input. Suppose you have say 2 or 3 interrupts, 2 or 3 interrupt inputs. Okay. Then given an interrupt line we can talk about the priority, and given this, okay, interrupt say we call this interrupt 1, interrupt 2 and interrupt 3. Suppose there are 3. Okay, to this we would be connecting the devices. Now, we can talk about a 2-dimensional priority structure. Now, generally what happens is the CPU itself will define the priority among these interrupt 1, 2 and 3. The CPU will define a priority, and then by this external arrangement on a given line, by hardwiring and daisy chaining and what not, okay, we can define the priority. So, you have a 2-dimensional priority. So, that also will be taken into account, okay, during the service. Good. And earlier I had also said that it is meaningful not to disable some aspect of the interrupt structure. Okay. Why? There may be some crucial inputs which you should never disable. For instance, power failure. In case power failure is indicated, okay, suppose we are able to disable the interrupt, then what happens? Before we can re-enable, the power may fail and we would lose everything that is in the semiconductor memory, no, volatile memory. So, generally what happens is certain inputs will be accorded the highest priority, not only highest priority, but also that it will not be masked, you cannot disable them. So, the term that is used for that is by disable or enable, okay, we can selectively enable, that is certain inputs, interrupt inputs will selectively enable, certain inputs will selectively disable. So, that particular thing by selection is called masking. Okay. Masking, and so we talk about maskable interrupts and non-maskable interrupts. Maskable interrupts and non-maskable interrupts. Now, for instance, crucial inputs such as power failure will all come under non-maskable interrupts. Meaning, suppose interrupt 1, interrupt 2, interrupt 3, they have a priority such that interrupt 1 is a highest priority. Generally, the highest one will be given the non-maskable character, generally. Okay. So, that it will never be disabled. Okay. Suppose we have 3 different priorities like this, then we may be selectively enabling this or disabling this, enabling this or disabling this, whichever way you want. That is, at any time I can selectively enable interrupt 1, interrupt 3 alone, interrupt 2 is disabled, or any other combination. Interrupt 1 is enabled, interrupt 2 is say also enabled, interrupt 3 is disabled. So, how is it done? Obviously, to the CPU we have to send the appropriate command, and that command, okay, that command word will have the appropriate bits like masking or non-masking. So, it is nothing but what we knew as configuring. Okay, earlier remember we were talking in terms of peripherals, we are talking about configuring and then data transferring, that is configuration phase. So, selectively masking any interrupt, so non-maskable you just cannot do anything, it is whenever an input comes or non-maskable interrupt, it will be responded to by the CPU. Sometimes it may be so critical that even the interrupt instruction cycle may not be completed, but anyway, as far as interrupt, if it is called an interrupt, the instruction cycle must be completed. Okay. Now, during configuration phase we may selectively mask, that is meaning selectively enable and disable certain interrupts. Non-maskable cannot be touched at all, and generally these non-maskable interrupts are used for very critical things such as power failure, okay, some other system failure aspects. Good. This is about what we need to see about interrupt in general. However, while talking about the interrupt and the interrupt handler, okay, that is a service routine, I would like to touch upon a few other aspects also which are related to it. Okay. Essentially, interrupt is carried out through a context switch, we saw that, right. Now, we saw that a device is interrupting. Okay. Now, it is also possible that interrupt can be achieved by executing an instruction. It may sound a little strange, because there are some interrupt instructions. Okay. So, we talk about like this, the main routine is executed and then some situation arises and the CPU cannot proceed further. Now, that situation may be because a device is interrupting, or because the CPU has come across an instruction which is called an interrupt instruction. Okay? There are some software, we call these as software interrupts, though all the time we have been talking about an interrupt and it is through hardware and so on. There are software interrupts too. Now, similar situation may arise, even a call to a subroutine is somewhat like that. Okay? A call to a subroutine is, the main routine is interrupted and the subroutine is taken up. So, similarly, the software interrupt also, execution of software, that is an appropriate instruction. Then some situation may arise, for instance, an instruction which is not part of this particular implementation of the processor, right. That is an instruction which has been reserved for future processor, but not for this version. Suppose the instruction comes, then it is really an illegal instruction, the processor cannot proceed. Or say in division, divide by 0 if it comes, the processor cannot proceed. So, like this the processor may get interrupted, and we say in general a flag such as an exception flag is raised. Okay? That is, an exception has arisen and the processor has to respond to that exception. It is similar to the interrupt. Now, if we know precisely what are the exception, we can also store the routines or handlers for these exceptions. So, the interrupt handler and exception handler. What is an exception? Exception is essentially something which the processor cannot proceed with, and instead of going rule by rule, now an exception has come, the processor has to respond to that. Okay, similar to that. Now, exception, there are two types of exception. One is processor exceptions. Okay. The other one is in fact called a programmed exception. This programmed exception is similar to the software interrupts I was mentioning, okay, essentially through software. Say for instance, a software interrupt, programmed exceptions are like this. Now, let us see what is the processor exception. That is, the processor cannot proceed further. Why? The programmed exception is specifically through some instruction or other. But the moment we say software, it is something which is acceptable by the processor. That is essentially some instruction. Now, what is this processor exception? This we will see in detail. It is similar to the response by the processor will be similar to what it would otherwise do in the case of interrupt. Okay, that is why we are taking it up. Now, there are essentially three types we can talk about in general. One is a fault. Okay. Fault is a processor exception. Now, what is a fault? Yeah, we had come across this, have we not? A page fault, a segment fault. What is it? The page is not accessible to the processor. The segment is not accessible to the processor, because mainly the memory is not holding what the CPU wants. Now, what is the situation? What is the remedy for that? The CPU has to bring in the new page or bring in the new segment, okay? And then after it has brought in, whatever the CPU requires, the CPU can continue with the same instruction. Meaning, an instruction has come across an address, and that particular address, the contents of that address is not available in the memory. This is what it is. Okay, good. So, after then we say that say a page fault. Okay, a page fault. So, the processor comes across a page fault, then we say an exception is raised, and this is a fault exception. So, a page fault handler, okay, is a program that is run, and then that sees to is that it swaps out one of the pages and swaps in a new page, whatever is required, and at the end of it the processor can resume from where it left off, right. So, after we say after servicing the fault, okay, after servicing for whatever fault, after servicing, the CPU resumes with that instruction. We will say resumes. The CPU resumes with the instruction which caused the fault, right. Now, there is another type of exception called a trap. Now, why are we talking about this? Because they are all similar, interrupt handler, then we talk about a fault handler which is coming under exception. Now, we will talk about a trap handler is another exception. The CPU cannot proceed, it is getting disturbed or interrupted, okay, but it is not the same as interrupt. So, there are different names for it, that is why. Now, what is a trap? The trap handler is for instance, power failure we were talking about just some time back. Okay. Now, we say power failure causes the CPU to be trapped, meaning the AC power is dipping and DC power will go off in another few milliseconds maybe, and before that a few instructions will be executed, and those few instructions will possibly for trap handling, okay, meaning bring it to satisfactory, or rather bring it to a logical portion, that is, let us say end of that current instruction and stop, maybe a few instructions are necessary, okay, and then stop, save everything, so that later on, okay, when the power comes back, when power resumes, the service can be restarted with what? With of course the next instruction, okay. Now, in the case of fault, after servicing, the CPU resumes with we can in fact write with the instruction which caused the fault, correct, with the instruction which caused the fault. Now, in the case of trap, after servicing, yes, after servicing CPU resumes with the next instruction. Why? Because a trap is a situation which with which the CPU cannot proceed any further. So, it will be brought as that is, it is a it's a legal instruction, but because of power failure and something like that, it cannot proceed, right. So, it will complete that instruction, and so the CPU resumes with the next instruction, okay. So, this is important. Now, here it is the with the same, we can in fact emphasize with the same instruction, right, with the same instruction which caused fault. Now, here it is the with the next instruction. So, you can see there are some minor differences. Then there is another type called abort. That is, a situation arises and the CPU cannot proceed any further. So, it has to abort, in other words the CPU stops, okay, and abort handler causes the CPU to stop and it cannot proceed any further. That is, it is not like a fault where some corrective action can be taken and we can proceed with the next instruction. It is not like a trap where the current instruction can be executed and then we can proceed with the next instruction. Here the CPU cannot proceed any further because of the situation, right. There is no correction that is possible. So, we have got a fault handler, we have got a trap handler, we have got an abort handler and interrupt handler, okay. So, this in fact is somewhat related. In both these cases, the CPU stops and takes up some other service. Now, specifically we were talking about device interrupt service here. Here these are all internal, the processor itself faces these. In addition to this, as part of the program, by including appropriate instruction in the software, right, we can also cause similar to interrupt. But all these are, that is processor or programmed, these are all internal to the processor, right, unlike in this, in which the external device is involved. Okay. So, in the next lecture we will briefly take a look at the DMA and then proceed to trace the evolution of I/O over these few years.